Okay, so from my last video, hopefully you have a better visual of continuity on a graph and discontinuities and what makes something continuous. Never forget this, okay? That is what proves whether something is continuous at a point or not. Let's get into it algebraically. Here's a function. Here's a piecewise function. And we have ourselves a positive x squared function when x is less than 2, and a negative x squared function when x is greater than or equal to 2. So if we want to do this, if we want to prove, we want to see does the limit of our function as x is approaching c from, well actually our c is 2 in this case, right? Right there's our 2. So that's the breakpoint. That's where we want to see if it matches up or not. So back to the color, what do I have, green? Oh, that's yellow. So from the left, we want to know, does that equal, well, if 2 is my c value, f of 2, we figure out what that is. And then is it the same y value on the right side? Well, first thing we got to do is figure out what function, what f of x do we use when we're on the left side of 2? When we're on the left side of 2, that's when x is less than 2. So we want to use this function. We want to use the limit as x is approaching 2 from that side. This is the function we use. That's the function we use on that side of 2. Well, notice here that right here is the equal sign. This is the function you use when x equals 2. So what is f of 2? F of 2 is this. It's negative, well, 2 times 2 is 4, and then we have, that's 8, and that's a minus 2. We'll figure that out in a minute. By the way, I should have done this. We don't know really if it equals each other. We're about to figure that out right now. On the right side. The right side is when x is greater than or equal to 2. That's the function we use on the right side. So when x is approaching, here I wrote c again, I meant to write 2. When x is approaching 2 from the right, the function we use is negative x squared plus 4x minus 2. And yes, if it haven't figured it out, we're going to get the same value for that as we are for this, because we're going to just do the same thing. We're going to take that 2 and plug it in here and here, just like we did here and here. Let's evaluate this thing. So when you plug in a 2 here and here, you're going to get 2 times 2, you're going to get 4 minus 8 plus 6. That's negative 4. That is a 2, a positive 2. Does that equal... what is this, 8? Well, that's a negative 4, negative 2. That's 8 minus 6. That's a positive 2. Let's see, does it equal this? Well, it's going to get the same value, right? Because don't we do the same thing? We're going to have negative 4, excuse me, and then we have 8, and we have a minus 2. You're going to get the exact same value. Look at that. It is continuous at x equals 2, because all three of these are the same value. I'm not going to spend lots of time in this video on graphs, but just to tie it into our last graph. Okay? This is what's happening at 2. What happens is the y value is 2 for everything. When you're with the positive x squared, here's the positive. Remember positive x squareds, but we only use it on this side of 2. And then this is a negative x squared. Don't forget negative x squareds are these ones like this. But we only use that part of it up to 2 on that side, and they actually both meet at 2. And so not only does the limit exist at x equals 2, but it's also continuous at x equals 2. Now for this one, this f of x, we have another piecewise function, and I'm just going to leave this up here as a gentle reminder because that's what we do all the time. All right, well for this f of x, let's see, we've got the limit as x, again, 2 is our breakpoint, so we want to see does this function meet up at our breakpoint there when 2 is on the left side? Just to save time here, when x is greater than 2, this is to the right. Over here, this says x is less than or equal to. Yes, this is it does equal it, but it's also on the left side and equals 2, right? Sometimes it depends on which function they tell you to use when x equals 2. Sometimes they'll tell you to use this one. Sometimes they'll tell you to use that one. You just follow the directions. Okay. So let's get back to this. So on the left-hand side, we are going to use the function negative 2x. I'm just going to plug it in. Okay. We want to see if that equals f of 2. And we want to see if that equals the limit on the other side, the right side of 2. What do we use on the right side of 2? We use this function on the right side of 2. We use x squared minus 4x plus 1. Let's evaluate. Plug in that 2 right there. You're going to get negative 4, right? 2 times negative 2. Well, does that equal, what's f of 2? F of 2. Well, right here is what we use when x equals 2. So this is the function we use, so f of 2 would look like this. Right. On the right side of 2, I think you see over here we use the quadratic function. So we plug in our 2, and what are we going to get? We're going to get 2, I'm sorry, that's 4. Let me just write that down. 4 minus 8 plus 1. So we have a negative 4, we have a negative 4, and what is this? This is, oh, that doesn't match up. That's 5, that's negative 3. Aha, so notice how even though these two equal each other, it does not equal this side right here. So all three of these have to be the same y value for it to be continuous, and so therefore this one is discontinuous at x equals 2. Okay? So they don't match up. One's going to negative 4, one's going to negative 3. Now I was going through some of the examples on Delta Math, and this is tricky. I just want you to be mindful of it. It's not a hard question, but it's not what you would assume. So say I gave you this problem right here. Say that was on Delta Math. I ask you a problem and you do it, right? And we always talk about, well, the function, this right here is it's a straight line, and this is a parabola. Those are continuous all over the place. So the only real question is where they meet up. Where, are they continuous where they meet up? But sometimes they might throw a little twist in there and ask you, well, here's your f of x right here. It's the same, this is our f of x. But what's the answer to this question? Well, how would you answer it? Well, the first thing you got to do is figure out x is approaching 3. Well, what function do we use when x equals 3? You don't need to worry about this, because look at this, x is greater than 2. All right, that means that whenever x is 3, this is the function we use. So if x is approaching 3, this is the right of 2. All you do is this. This is the same thing as saying the limit as x is approaching 3. Well, you just have to determine which function do we use, right? See, it's a little tricky, but once you figure that out, it's not hard at all, because all you're going to do now is just, well, plug in your 3 here, and you're going to get 9 minus 12 plus 1. That is a negative 2. Okay? So the math is usually not difficult. Just be mindful of what x value they're asking you to approach. They will get a bit trickier, but again, so long as you remember this golden rule of what makes a function continuous at an x value, I don't care how hard they get, you just follow the same pattern. So here's my g of x right here. I'm going to leave it down here so we can do the work up here. I'll do it in white right now. All right, so first let's look at this piecewise function and determine what's on the left and the right. So x is less than 1 is on the left of 1, and this is the right. And if you notice, when x equals 1, this is also when x equals 1. That's what you use. So we have the limit as x is approaching 1 in this case. Well, from the left-hand side, it has a variable, k times x minus 4. Just plug in, we're following the same pattern. All right, so f of c. Well, f of c in this case would be f of 1, right? Let me just plug that in, we'll get to that in a moment. What is the limit as we are approaching 1 from the other side, the right side? Well, the right side, notice how we use this one right here. 3x squared. Okay. Now you still do here we'll work right to left just because this one doesn't have a k in it. So what do you do now? You don't change what we do. We take the 1 and we plug it in there. Again, I should put this, we don't know if they equal each other. You plug a 1 in there, you're going to get 3. What about this one, f of 1? Well, again, when x equals 1, that's what we use. So you're going to get the same value. You're going to get 3. What about over here? Well, what did we do? We took the x value and we plugged it in. Just because we have a k doesn't mean we don't plug in the 1 for x. We still do that. And when you plug in a 1 for that, you're going to get this. You're going to get k times 1 minus 4, which is just k minus 4. I said that we need to put this, I forgot that we're not trying to see if it's continuous. The question is saying this. Solve for the constant k such that h of x, oh, I forgot, I didn't change it over here. This is g of x. Anyway, let's just change it here. I thought I had h of x, but we use the g of x, so just call it g of x. Our goal here is we want this to be continuous, okay? So what constant k would make this g of x continuous? Well, maybe you have an idea of what to do. This already equals each other, right? So apparently we need this to be a 3, this to be a 3, this to be a 3. So basically, we need k minus 4 to equal 3. If that equaled 3, then everything's good. Well, what would make that equal 3 if k were 7? Ta-da! So if you want to just check yourself, look at this. So if that k were a 7, we'd have this. Let me just change it to blue here. We would have the limit. I'm just checking myself right now. If that k were a 7, it would be 7x minus 4, right? What happens when you plug in a 1 there? That's right, you get 3. Okay? So we're looking for k equals 7. Now for solving k that's a bit trickier, okay? Notice here it doesn't say greater than or less than. It just says strictly if x equals negative 7, we're going to call it k. But if x does not equal negative 7, we're going to use this rational function. All right, so first thing I'd like to do is set up our limit. So we have the limit as x is approaching. So here the question in this piecewise function is negative 7. So we're approaching negative 7. We want to see if it's continuous there from the left of our function. Does that equal the same thing as f of negative 7? Oh wait, we're going to find the k, so we don't have to put a question mark there. We're just going to figure out what that k value is. And let's see here. So on the limit as x is going to negative 7 from the right side, well, what do we use from the right side? This says whenever x does not equal negative 7, we use this function. So x does not equal negative 7 here, and it does not equal negative 7 here. It only equals negative 7 there. So we use the same function. Okay, we use that rational function. Let me get rid of a little bit of this here. Okay, there we go. And then I'll put in my f of x. So let's clean this up. We have the limit as x is going to negative 7 on the left side. We use x squared plus 6x minus 7 all over x squared. You can see it. I'm just copying that down. What are we using when x equals negative 7? When x equals negative 7, our f of x is k. It's a constant. It's sort of like saying f of x equals 4. All right, so if y equals 4, in this case y equals k. So it equals k. And on the other side, we have the same thing. We have x squared, 6x. I'm not going to say it. You can see what we're doing here. All right, now, what you're first going to do, what you should do, is you should take your negative 7 and you should plug it in here, here, and here. So what does happen? Hold on. We get ourselves 0 over 0. You may remember 0 over 0. We have to do something. Since we have two quadratics, this makes sense. Let's factor them out. Positive 6, how about a negative 1 and a positive 7, right? That's right. And then over here we have x, and we need a positive 7 and a negative 5. Okay, so what can we cancel out? We get to cancel out an x plus 7 with an x plus 7. And guess what? We're going to do the same thing over here. So watch what this comes out to be. Let me just make this smaller. We now have the limit as x is approaching negative 7 from the left. We're left with x minus 1 over x minus 5. And guess what? We have the same thing over here. I'm just repeating it, but I want to follow the pattern. On the right side, we're going to be left with the same thing, x minus 1 over x minus 5, right? Because we're going to factor out the same factor, x plus 7. Next, we can plug in and get a value. Negative 7. Well, that's going to be what? Negative 8 and negative 12. That's a k, and well, that's going to be the same thing. That's going to be positive 8/12, right? Because the negative cancels. So basically, Guess what k has to be? K has to be 8/12. If you want to reduce it, great, go ahead. What is that? 4? No, I'm sorry, we want 2/3, right? Okay. K equals 8/12 or 2/3. We haven't focused on many graphs here, but I just want to show you what's happening. We just canceled out x plus 7, which means at x equals -7, we have a hole. If you were to plug this into your calculator, this is what you're going to see. Okay, here's the function. And yeah, there's an asymptote here, but my question was, as we're approaching -7, okay? -7, well, the limit exists at -7, and what happens is you're approaching 2/3, right? That's 0.6666 right there. If f of -7 also equaled 2/3, well, then this would be a continuous function, because then basically what you're doing is this would also equal the same value, and then it would be continuous there. Okay, let's wrap this video up by seeing if we can look at these three functions, and what am I asking you to do here? We're going to solve for any x values, if any, they may not exist, that would make the functions below discontinuous. And if so, we want to classify the type of discontinuity, meaning infinite, removable, one of those, jump. Okay. Well, f of x, let's start with this one. We have a fraction. Can x equal 0? Yes. Y would equal -3/2. Can x, so what can x not be? Well, the only thing we have to be mindful is what makes our fractions undefined. The only thing that makes a fraction undefined is when our denominator equals 0. So we cannot have x minus 2 equaling 0. What would make that happen? Well, we can't have x equaling 2, because if x equaled 2, we'd have a problem. So it is discontinuous at x equals 2. All right, we have a break in the graph. We can't have x equals 2. So what is there? Is there a hole? Is it an asymptote? Is it a jump? What happens when you have a fraction that is undefined and you cannot get rid of that undefined issue? I want to change the color. You have a vertical asymptote there, okay? And if you were to plug this into your calculator, you're going to see that it does something like that. This right here it is discontinuous at x equals 2, and I guess I should write it down here, it doesn't matter. It's infinite discontinuity. All right, there's the first one. Let's take a look at the second one now. Oh, well, we'll just get rid of that. All right, let's just clear that off and do that. The video's almost over. G of x. Well, g of x, now what is that? That is x squared, that is x squared minus 2x plus 1. Well, is there anything in the denominator that's going to be undefined? Can we, if x is a 2 or 3 or -8 or, well, guess what? This right here is a polynomial, and I want you to memorize this because we're going to use this fact in the next topic, intermediate value theorem. Polynomials are continuous everywhere. This is a polynomial, and if you think about why is it continuous everywhere, well, the simple fact is there's nothing in the denominator that's ever going to make it undefined. You can plug in any x value forever and ever and ever and get an answer. And if you think about this, this is nothing more than a parabola, and it looks like that. And guess what? It's continuous in every single point going from positive infinity to negative infinity. It is continuous on every single x value. So whenever you see a polynomial, nothing's going to make it discontinuous. Use this fact. Polynomials are continuous everywhere. That's going to come up again. Last but not least, h of x. So h of x, at first glance, you might say, well, yeah, 1's a problem. Well, is it only 1? Let's do this. We cannot have, well, I don't know why I did that. We're going to do this. We can't have x squared minus 1 equaling 0, right? That's a problem. That's a no-no. Well, this right here is a difference of two perfect squares. X plus 1, x minus 1, which technically means that we can't have either one of these equaling 0 because 0 times anything is 0. However, if we go back to the problem over here, we can cancel something out. If we factor the bottom here, like we just did over there, we could do this. That will cancel with that, and I'm left with an h of x that equals 1 over x minus 1. So notice how we were able to remove this problem right here, all right? At x plus 1, we remove that. When you cancel a common factor out, that means you have yourself a whole. And you're going to have a whole at x equals negative 1. When you have a whole, that is known as removable discontinuity. Refer to one of my earlier videos. And at the final right here, well, we cannot get rid of that problem, so no matter what, x equals 1 is a problem. There's a vertical asymptote there, which means we have infinite discontinuity. Infinite, okay? To wrap up, this video right here will help you finish up the algebraic piece on homework 6, as well as page 79. Don't forget to classify all discontinuities. Thanks, have a great day.